Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries, where we make AI practical, profitable, and human. Today, we are on day 19 of our hashtag 30 Days of Code challenge with Educative, and today's problem is stream of characters. Let's get into it.
Today, we're tackling one of the most conceptually interesting streaming problems on LeetCode, called stream of characters. Now, this problem has a reputation. A lot of people find it confusing at first because it combines three tricky concepts: real-time streaming data, suffix matching, and tries. And here's the thing, the naive solution looks totally reasonable, but it's way too slow for production use. So today, we're going to start from scratch. We'll build the slow version first so you understand why it fails. Then, we'll walk through the mental breakthrough that turns this into an elegant, fast solution using a reversed try. By the end of this video, you won't just know how to solve the problem, you'll understand the deeper pattern of transforming hard problems into easier ones. Let's dive in. Alright, let's strip away all the LeetCode jargon and talk about what this problem is actually asking. Here's the setup. You're given a fixed dictionary, just a list of words like from left to right in the array, CD, ABC, and F. Then, characters start arriving one at a time, kind of like someone typing in real time or messages appearing in a chat stream. So you might get A, then B, then C, then D. After every single new character, you need to answer this question. Does the stream of characters, as it exists right now, end with any word from the dictionary? Notice the word end. We're not looking for the word anywhere in the stream. We're checking if the stream's suffix, the tail end, matches a dictionary word. This is called an online problem, which means you can't rewind or restart the stream. You're processing it in real time. Let's walk through an example. Dictionary from left to right in the array would be CD, ABC, and F. Stream arrives, so you get A, then B, then C, then D. After A, suffixes are just A. There's no match here. After AB, suffixes are AB and B. There's no match here as well. After ABC, suffixes are ABC, BC, and C. Wait a minute, we have a match. ABC is in our dictionary. After, we check ABCD. Suffixes are ABCD, BCD, CD, and D. Wait a minute here, we have another match. CD is in our dictionary. So the core challenge is, how do we efficiently check if the current stream ends with any dictionary word? Thousands of times in a row. Okay, so how does LeetCode actually frame this? We need to implement a class called StreamChecker. When we initialize it, we give it our list of dictionary words. Then, there's a method called query with the parameter of letter that gets called over and over again. Each time it's called, we receive one new letter. And we need to return true if any dictionary word matches the stream's ending right now, or false if nothing matches. Here's what makes this challenging. The queries function will be called thousands of times, maybe 10,000 or more, so it has to be fast. We need some kind of internal memory to remember all the previous letters because each new letter builds on what came before. The dictionary could be large, so hundreds or maybe even thousands of words could be in that dictionary. Words could be long, up to 10 or 20 characters each. So if we use a slow algorithm, we'll time out. Performance really matters here. All right, let's start with the most natural first instinct, the approach most people think of immediately. What if we just store the entire stream as a growing string? Here's the logic. Start with an empty string S. Every time a new letter arrives, append it. S equals S plus letter. Then, check every word in the dictionary. For each word, see if that word matches the last few characters of S. If any word matches, return true. This is completely logical. It's how a human would think about the problem. You're literally checking, does my string end with this word? And yes, this absolutely works. On small test cases, it'll pass. It's simple, it's direct, and it's readable. But here's the problem. It's extremely slow when the data set gets large. Why? Well, we're about to find out. Let's write out the naive strategy in simple pseudocode so we can see exactly what's happening. Keep a string S that stores the full stream. When we initialize, store the dictionary, set S equals empty string. When query of letter is called, append the letter to S. For each word in the dictionary, get the length of that word. Call it L. If S is at least L characters long, extract the last L characters from S. If those characters equal the word, return true. If we checked all words and found no match, return false. This is exactly what the problem asks for. We're checking every word size suffix of the stream. It's brute force, but it's honest brute force. And here's what that naive solution looks like in actual Python code. Notice how clean it is. We're using Python's negative indexing to grab the last L characters, self.stream of -L onward. For small inputs like 5 words and 20 queries, this runs fine. But submit this to LeetCode on a large test case, you'll get the time limit exceeded error. So why does this fail? Let's do the math. Let's define some variables. Q, which equals the number of queries, how many times the query method is called. D, which equals the number of words in the dictionary. L, which equals the maximum length of any word. For every single query, here's what happens. 1, we loop through all D words. That's O of D. 2, for each word, we compare up to L characters. That's O of L. So each query costs O of D times L. And if we do Q queries total, the overall time complexity is O of Q times D times L. Let's plug in realistic numbers. So let's say Q equals 10,000 queries, D equals 1,000 dictionary words, and L equals 10 max word length. That's 10,000 times 1,000 times 10, which equals 100 million operations. 100 million character comparisons. That's way too much. And notice the real problem. We're rescanning the entire dictionary on every single query. We're doing the same work over and over again. There has to be a better way. Okay, let's step back and look at the structural pattern hidden in this problem. What are we actually doing? We're always checking suffixes. After each letter, we're asking, does the stream end with any of these words? Suffix checking is historically kind of annoying. Suffixes are harder to optimize than prefixes. Why? Because we have amazing data structures for prefix matching. specifically tries, also called prefix trees. But we don't really have a good data structure for suffix matching. So here's the breakthrough question. Can we transform this suffix checking problem into a prefix checking problem? If we can do that transformation, then suddenly we can use tries, and tries make everything fast. This is the major insight. And yes, we can absolutely transform this problem. Here's how. The key observation is we need to check if any dictionary word appears as a suffix of the stream. That's hard to do efficiently. But here's the insight. If we reverse all dictionary words and build a trie from them, then we can check suffixes by walking the stream backwards and checking for prefix matches in the trie. Let's see this with a concrete example. So our dictionary is ABC. Our stream so far, ABC. The question here is, does the word ABC appear as a suffix of ABC? Yes. How we solve it? First, reverse the dictionary word ABC. That becomes CBA. Second, build a trie from CBA. Third, when the stream is ABC, we walk it backwards. C, then B, then A. As we walk backwards, we traverse the trie. C goes to B, B goes to A. If we reach the end of a word in the trie, we found a match. This is the entire solution in one idea. Reverse all dictionary words. Walk the stream backwards. Check for prefix matches in the reverse trie. This transformation is the real algorithmic insight. Alright, but what even is a trie? Let's demystify this. A trie, spelled T-R-I-E, sometimes called a prefix tree, is just a tree data structure where each edge represents a single character. Each path from the root spells out a prefix of some word. We can mark nodes where complete words end. So here's an example. If we insert the words cat, car, and dog, the trie looks like this. Root at the top. On the left side, you'll see C-A-T. And then branching off from A, you'll see R. And then on the right side, you'll see D-O-G. The check marks mean a word ends here. Why are tries useful? Because you can check if a word exists or if a prefix exists in O(L) time, where L is the length of the word. You just walk down the tree character by character. And that's way faster than scanning through an entire dictionary. For our problem, we're going to build a trie of reversed dictionary words. Then for each query, we'll check if the reverse stream matches any prefix in that trie. Okay, so here's how the optimized solution is structured. We need two things. 1, a trie of reversed words. Instead of inserting hello into the trie, we insert OLLEH. Instead of ABC, we insert CBA. 2, a buffer that holds recent stream characters. We don't need to store the entire stream forever. We only need to remember the last max length characters, where max length is the length of the longest word in the dictionary. Why? Because if the longest word is 10 characters, we'll never match anything longer than that, so we can safely forget anything older. We'll use a DQ, double-ended Q, for this buffer because it lets us add characters to the front in O(1) time. For each query, here's what happens. 1, we add the new letter to the front of the buffer because we're working in reverse. 2, if the buffer gets longer than max length, remove the oldest character from the back. 3, walk through the trie using the characters in the buffer. 4, If we hit a node marked as a complete word, return true. This is way cleaner than scanning the whole dictionary. Let's write out the optimized strategy in pseudocode. And here's the full Python implementation. So what's happening here? We're using reversed of W to flip each word before inserting it. We're using append to left to add new characters to the front. We walk the try and check node.is_word to see if we've hit a complete word. This passes all LeetCode test cases easily. Let's compare the naive approach to the optimized approach. Here's the naive approach. Our build time is O of 1 because we just store the list. Per query is O of D times L. We scan all D words, comparing L characters each, which gives us a total of O of Q times D times L. Our optimized try approach gave us a build time of O of D times L. We insert D words of length up to L into the try. Per query, O of L. We walk at most L steps in the try, giving us a total of O of D times L plus Q times L. Let's use realistic numbers. So D equals 1,000 words, L equals 10 max length, and Q equals 10,000 queries. The naive total gives us 10,000 times 1,000 times 10, which gives us 100 million operations. The optimized total gives us 1,000 times 10 plus 10,000 times 10, which equals 10,000 plus 100,000, which equals 110,000 operations. That's roughly 900 times faster. The try approach completely changes the game. So let's talk about why reversing everything is such a breakthrough. The original problem, does the stream end with any dictionary word, is suffix matching, and there's no great data structure for it. You'd have to scan everything manually. The transformed problem, does the reversed stream start with any reversed dictionary word? This is prefix matching, and tries are perfect for this. Here's the key insight. We didn't try to force suffix logic into a data structure that doesn't fit. We transformed the problem so that the right data structure becomes obvious. This is a fundamental algorithmic mindset. When the problem is hard, see if you can reframe it into a problem that's easy. This pattern shows up everywhere. Suffix arrays versus tries. Two-pointer problems, reversing direction. Dynamic programming, bottom-up versus top-down. The skill isn't memorizing tries. The skill is recognizing when a transformation unlocks the right tool. Now, this optimized solution also handles several tricky edge cases really elegantly. One-letter words, the try handles these just fine. Single character nodes with is_word equals true. Duplicate words in the dictionary, that doesn't matter. The try merges them automatically. Words with shared suffixes. The try naturally shares prefixes which were suffixes before we reverse them. Streams where no match ever appears. We just return false every time, and no wasted work is here. Very long streams. We only keep max length characters in the buffer, so memory stays bounded. Empty dictionary or empty string. They're edge cases, but the logic still works here. The beauty of this approach is that the data structure handles complexity for us. We don't need special case logic. All right, let's zoom out and talk about the real mental model you should take away from this problem. Step 1, always start with a naive solution. Understand what the problem is actually asking. Build the slow version first. Be honest about why it's slow. Step 2, identify the shape of the repeated word. Here it was suffix checks. We were scanning the same dictionary over and over. Step 3, ask if that shape can be transformed. Suffixes are hard. Prefixes are easy. Can we reverse the problem? Step 4, choose the matching data structure. Once we transformed suffixes into prefixes, tries became the obvious choice. Step 5, build the optimized version on top of the transformation. Reversed words plus try plus buffer equals fast solution. This is real algorithmic thinking. It's not about memorizing that stream of characters uses a reverse try. It's about understanding why that works and being able to apply the same transformation pattern to other problems. And that highlights the real difference between memorizing solutions and actually learning to solve problems.
And that's a wrap for day 19 of our hashtag 30 Days of Code challenge. If you like this video, like it down below, share it with a friend, subscribe to our channel, and we hope to see you again tomorrow. Bye.